This is a little animation showing what we mean by half-life or rate of radioactive decay. Here, the red dots show a large number of identical atomic nuclei that all obey the same decay law. Let's just start this to show how this nuclei undergo radioactive decay. I've started it, and you can see as the red dots disappear, it's indicating that those particular atoms have undergone radioactive decay. And this graph here is showing the rate of decay. And as it turns out, all isotopes, radioisotopes, follow the same rate law or pattern. That means, and it's called first order rate kinetics, and it decays in this way. And because they all follow the same rate law, we can say that we can identify the half-life, the amount of time it takes for half of the radioisotopes to decay. So in this case, the half-life was 50 seconds. And so you could see if you go about halfway down to 50 seconds, maybe right here, let's see, whoops, we're having some problems with this. But anyway, it would be about right here. You can see 50 seconds would be half. And then in another 50 seconds, half of that sample would decay. And in another 50 seconds, half of that original sample. So if we increase the half-life to 100 seconds and restart the decay, you can see that the rate is slower. So the longer the half-life, that means it takes that much time for half of the original sample to disappear. So you can see that this is decaying the same rate law, but the time is longer for half of it to decay. So different radioisotopes have different what's called half-lives. They can be very, very short time spans or very, very long time spans, depending on the radioisotope. They all decay using the same rate law. It's just the time that the unit on the horizontal axis will be different. Okay, let's go back to our... So the half-life, by definition, is the time required for the level of radioactivity to fall to 1/2 of its value. In the examples that we just saw, we saw a half-life of 50 seconds and a half-life of 100 seconds. In both cases, the graph looked like this, which is what we call first-order rate kinetics, but the time scale was different. And in this particular example of plutonium-239, the half-life is the amount of time it takes for, they're saying this is 100% of the original sample, the time it takes to fall to half the original amount right here, if you go down, is 24,000 years, 24,110 years. So that means if you start with, say, 100 atoms, in 24,110 years, you'll end up with 50 atoms. And then the next half-life would be another 24,110 years. That would get you up to 48,220 years before you have, again, half remaining. So 1/2 times 1/2 is 1/4. And then half of that again would be 1/2 times 1/4 would be 1/8 remaining, about 12.5%, all the way out at 72,000 years. So you can see that the curve looks the same, but the time scale is different, and the rates are given in most widely expressed in terms of half-lives. So half-life, the time required for the level of radioactivity to fall to 1/2 of its value. And so here's just some different isotopes so you can get a feel for the wide variety of half-lives. So for example, uranium-238, the one that's found in the soil, the half-life is 4.5 times 10 to the 9th years. Okay, that's 4.5 billion years for half of the original sample to decay. Potassium-40, 1.3 times 10 to the 9th years. That's why we have radioactive potassium isotopes still mixed in with a regular sample of potassium. Whereas polonium-214 has a half-life of only 0.000016 seconds, so that doesn't stay around for very long. So this is how we could explain, even though we have in nature radioactive isotopes, we know they're undergoing spontaneous radioactive decay. If that's the case, you may ask yourself, why do we have any of those isotopes remaining? The reason why is because the decay rate in some cases is very, very slow. Okay? And in some cases, it's very, very fast. All right, so let's practice that to predict how much radioactivity would remain, or how much time. In this case, tritium is sometimes formed in the primary coolant water of a nuclear reactor, and it's a beta emitter with a half-life of 12.3 years. So for a given sample containing tritium, after how many years will only about 12% of the radioactivity remain? So given the half-life, the question is, how long will it take to only have 12% of the original value? So from here we know that one half-life, and the abbreviation is T1 half, that commonly T1 half is equal to half-life. So after one half-life, that means half of the sample remains. And in this case, that would be 50% of the sample would remaining. And then after two half-lives, only 1/4 is going to remain, and that would be 25% remaining of the original sample. After three half-lives, that would mean 1/8, because it's 1/2 of 1/4 would remain, and that's about 12%. So it's 12.5, but they said about, so about 12%. So if we're estimating here, one half-life takes 12.3 years. So it would be 12.3 years plus 12.3 years plus 12.3 years, or 3 times 12.3 years equals about 36.9, which is about 40 years. So I would say, to answer this question, after about 40 years, 12% of the radioactivity would remain. So this starts giving you a clue as to why nuclear waste from power plants is a problem, because you create all of these radioactive isotopes. It takes varying amounts of times for those isotopes to no longer be radioactive. Okay, so let me here in closing give a couple of examples of some problems with some particular radioisotopes. First of all, iodine-131. Iodine-131 itself is a beta emitter. It has a half-life of 8 days. And the problem with iodine-131 is that it is a fission product. So it's going to, it is a product of nuclear fission reactions. So it's found in nuclear fuel cells, and then the waste nuclear fuel cells that are still stored on site. It itself is water soluble, and iodine is a micronutrient that is needed for hormones in your thyroid gland. And so it collects iodine in your body. Once it's in your body, it collects in the thyroid gland. So the problem is that if iodine-131 accidentally gets into the environment, say from a nuclear power plant, it will dissolve in water, so it can get in the groundwater, and then it can be, if you happen to drink the water, or you eat something else that has drank the water and now has that iodine in it, then you could be exposed to this iodine-131, and it will collect in your thyroid gland. In small amounts of iodine-131 can actually lead to thyroid cancer, whereas high concentrations of iodine-131 are actually used for medicinal uses to treat thyroid cancer. Okay? See, in the high doses, because it's a beta emitter, it will just kill the tissue around it, and it will be just right in the thyroid. It doesn't penetrate very far, and since it's in the thyroid, it kills the thyroid tissue. It's actually a great treatment for thyroid cancer. But in small doses, it just does enough damage then to the thyroid cells that could then lead to mutant cells, which then leads to cancer. And so people who have been exposed to iodine-131, for example, from nuclear accidents, for example, Chernobyl, have been shown to have a greater incidence of thyroid cancer. So it's a good and a bad thing. And then radon-222, I promised I'd come back to that one. Radon-222 is an alpha emitter, and it has a half-life of only 4 days. It's a noble gas. So what happens with radon-222, since it is a decay product of uranium-238, and uranium-238 has a half-life of 4.6 billion years, although uranium is a very slow decay process. So that's why we still, even though the Earth is so old, we still have uranium 238 around, which is constantly undergoing this very slow radioactive process. Well, the problem is if a radon 222 happens to be produced and then seep out, once it's a gas, it can seep out of the ground. And then if you happen to be breathe in to your lungs uranium 222 and it undergoes radioactive decay, you can be bombarded inside your lungs with an alpha particle, which is going to do damage. Now, if it's not very much, it shouldn't be too big of a problem. But if you have a high concentration of it, it is a problem. And the other problem is once the radon 222 undergoes radioactive decay, it keeps decaying down to polonium. Eventually, it can get to polonium 210, which is a solid. So all the other decay products after radon 222 are solids. So then that particular radioisotope is going to be stuck in your lungs, and it's going to continue to undergo radioactive decay. Polonium is an alpha emitter as well, and it has a half-life of about 140 days. Okay, and so then it will further decay to other radioisotopes, which can then continue. One radon 222 can give one alpha emission, but then the decay products further down the line can continue to emit both beta and alpha, depending on what it is. That's why it's a problem if it gets into your lungs and it undergoes decay before you have a chance to breathe it out of your lungs. Okay, and so it's found obviously from the U-238, which is in the crust of the Earth. And so what has happened, people have found, is the radon 222 can collect in basements. And the decay product, like I said, is a solid. So a lot of times people will have radon detectors in their homes if they have a basement. And if they have high levels of radon, then they just have to install ventilation systems to keep circulating the air in their basements to make sure that the radon 222 passes right out of the basement. So anyway, that's just two examples of two radioisotopes, iodine-131 and radon-222, that can cause problems. And I think you can start seeing that nuclear waste can be a problem because nuclear fuel pellets have a large amount of uranium-238, and also a fission product is iodine-131. So those are just two examples of some of the problems with the leftover fuel from spent nuclear fuel cells. So we'll talk more about that in the next video.